Hello and welcome to this video podcast for human genetics. In this podcast, we're going to continue our discussion of multifactorial traits. What I want to talk about in this podcast is how we can predict whether or not someone will have a multifactorial trait and whether or not they can pass it on to their children. What kind of tests do we use? What kind of measurements can we take advantage of? Multifactorial traits aren't as simple as single gene traits. For instance, Huntington's disease, we know, is a single gene trait. We know that if a parent has Huntington's disease, there is a 50% chance their children will have it. Multifactorial traits are not quite that simple because there are multiple genes involved and there are environmental factors involved. So traits like asthma, heart disease, cancer, and many others are difficult to predict. So what do geneticists use to make predictions on whether or not somebody has or can pass on traits like asthma, heart disease, or cancer? So let's consider now how we are going to predict multifactorial or polygenic traits. And we're just going to touch the surface of this. You could take whole semesters, probably whole programs, on just learning how to make these kinds of predictions. And anyone who might be interested in a career in something like genetic counseling, this is what you would spend a lot of your time doing. I want to talk about two general numbers that geneticists will use to make these kinds of predictions. The first is empiric risk, and the second is heritability. I'm going to start with empiric risk and then I'll come back to heritability. So what is empiric risk? Well, first of all, before I define it, I want to tell you that it's a population statistic based on observations. It's not necessarily a pure calculation. And not to worry, you're not going to have to calculate an empiric risk, but you should know that it is a population statistic based on observations. More precisely, an empiric risk is a probability that a trait will reoccur based upon its incidence in a population. Probably a good idea to define what I mean by incidence. And this is just the number of new cases of a disease during a certain time frame in a certain population. Now this number, this empiric risk number, becomes more precise by narrowing this population. And I'll talk about that in just a moment. Now, what can cause an empiric risk to increase? In general, there are three ways that an empiric risk can increase: the severity of the disease, the number of affected individuals. This makes sense because the definition of empiric risk considers the number of new cases. And the last one is the relatedness affected individuals. So for instance, empiric risk would go up if within the population we're studying, we're looking at individuals within a family, as opposed to individuals within a general group within the population of unrelated individuals. And then within relatedness, you can also consider how closely individuals are related. As an example, let's consider the trait of a neural tube defect. An example of a neural tube defect would be spina bifida. So let's consider how the empiric risk can change based upon these parameters. So for instance, in the US, the empiric risk is 0.1%. Not super high. But if you narrow this down to, say, US population of English, Irish, or Scottish ancestry, that number goes up to 0.3%. Now that change in empiric risk doesn't seem like it's huge, but it does triple. So that is a pretty big increase. Now, if you look at a different population, you say U.S. populations where one sibling has a neural tube defect. I should have abbreviated that up here. When I say NTD, that's what I mean, neural tube defect. So when one sibling has a neural tube defect, then that empiric risk goes up to 3%. So that increases it by 10 times. So you can see by changing the population and considering how related the individuals are, the empiric risk changes. Your book discusses how the empiric risk changes for individuals with a cleft lip. If you want to, you can look at that. I won't ask anything specific about it, but that does offer a nice example of how the empiric risk changes based upon how closely related individuals are. Next, let's consider heritability. Now, remember, empiric risks include genetic factors and environmental factors. Heritability only considers the genetic influence of a trait or a disease. Now, there are many different statistical methods that are used to calculate heritability, and we're not going to go into great detail with that, but I would want you to know that a main factor in determining heritability is relatedness. For instance, the heritability of a particular trait or disease is going to be higher amongst first cousins compared to the general population, or compared to second or third or fourth cousins. So I want to write down some of these relationship percentages that you should know. So over here I'm going to put relationship, and then here I'm going to put the percent of shared genes between those individuals. So sibling to sibling. Any two siblings, myself to my brother, or myself to my sister, or myself to my other brother, we have 50% shared genetics. We each got 50% of our genes from our mom and 50% of our other genes from dad. So it makes sense that we have this 50% shared genetics. Now, parent to child, as I just said, we will have a 50% shared genetics with our mom, and then we'll have a 50% shared genetics with our dad. Now, why is this useful? Well, it's useful because it tells us how likely we are to have a particular trait. Now, this is true with every one of these that I'm going to say, but I just want to point it out here. If my siblings have a particular trait, then there is a 50% chance that I will share the genes that contribute to that trait. Remember, it excludes the environmental factor, so that trait may have something to do with the environment. So it doesn't mean I have a 50% chance of having the disease. It simply means I have a 50% chance of having any genes that might contribute to that trait. So let's make that as a main point down here. I'm going to put in parentheses, only considers the genetic component. For instance, one of my siblings had cancer. There's a 50% chance that I shared those same genetic factors that contributed to that cancer. However, my sibling and I have lived in different environments. We have done different things in our lives. And so it doesn't mean that there's a 50% chance that I too will get that kind of cancer. It's just a contributing factor that gets placed into trying to really understand multifactorial and polygenic traits. As I said, it's very difficult to make these predictions, and this is just one factor. So let's write down some of these other relationships. So an uncle or an aunt to niece or nephew, or grandparents to grandkids. These are both 25%. My uncle has a trait, there's a 25% chance that I will have the genetic component of that trait. Again, only the genetic component. First cousins, two first cousins, there is a 12.5% chance. And here, because I'm running out of room, I'm just going to write second cousins, third cousins, and fourth cousins. Second cousins, there's a 3.13% chance that I would have a shared genetic component. Then third cousins goes down to 0.78, and fourth cousins are 0.2%. Now, these numbers are used, as I said several times, to try to make a prediction of whether or not somebody will have a particular trait. But these numbers also give us a little insight to the history of why certain individuals with certain relationships aren't allowed to get married in some countries. And the reason for that is, let's say that cystic fibrosis runs in a family. And to have cystic fibrosis, you have to have the two little C alleles. Well, these little C alleles turn out to be pretty rare. They don't occur in the general population with a high frequency. And so within a family, you have a lot of individuals who are heterozygous. In fact, we all are heterozygous for various mutations that could cause diseases or other negative traits. They're just hidden as a heterozygote. Okay, so because we know we have these heterozygous traits, we know that the only way you're going to have a child that is little c, is if you have children with somebody who is also heterozygous, or they themselves are little c. Now, since this is a rare allele, this little c allele, the chances of finding a mate that looks like this increases in families. Now, you might be surprised to know, and maybe you know this from other classes, but in the United States, every state allows second cousin marriages. Now, there might be other reasons not to marry a second cousin, but as far as shared genetics, it is pretty low. And the chances of passing on a deleterious effect is not that much higher than in the general population. Now, if you happen to know people who are second cousins that are getting married, and there is a known genetic trait in that family, say like cystic fibrosis or Tay-Sachs, it would be a really good idea for them to be tested so they would have even a further understanding of how likely that is to pass on. I was actually surprised to learn that in about 50% of U.S. states, first cousins can get married. And so that means about 50% of our states, first cousins cannot get married. Now, in these 50% that allow first cousin marriages, some of them have restrictions. Like one of the first cousins has to be an adopted first cousin. Or the first cousins can get married only if they are beyond the age of having children, or if they are sterilized. But other states have no restrictions on first cousins getting married. Again, that 12.5% is a pretty steep number if something like this runs in the family. So if you happen to know anybody that are first cousins getting married, or if in your professional careers you encounter this, really stress the importance of having genetic tests done before they have kids. Now again, I've said it many times, I'll probably say it a few more times, this prediction of multifactorial and polygenic traits is very difficult. And we can use empirical risks and heritability to kind of get at those numbers. But to fine-tune those numbers even more, there are two groups of individuals that can be studied that help fine-tune those numbers, give us a better understanding of genetic and environmental contributions. And these two groups are adopted individuals and twins, both monozygotic and dizygotic. And we'll abbreviate those as MZ and DZ. But first, let's talk about adopted individuals. As we begin this discussion, let's consider the biological parents. These are the parents who placed the child for adoption, and the adoptive parents. These are the parents who took this child into their home and raised them. Now, by studying the biological parents and studying the adopted individual, so the adopted child here, we should consider these two things. One is that they have a shared genetics. From the last whiteboard, we know that the parents, the biological parents, share about a 50% genetics with the adopted child. However, they don't share the environment. So any trait that has an environmental link is not shared by these two individuals. And I should have said this at the beginning. For the purposes of our discussion, we're going to assume that the child that was placed for adoption was adopted by parents who are not related. I know sometimes grandparents and uncles and aunts adopt children, but these studies are really looking at unrelated individuals as the adoptive parents. Okay, so now let's think about what we can get from looking at traits in adoptive parents versus traits in the adopted child. First, they don't share genetics. I mean, except from the fact that we all share a common genetics, but they don't share a relatedness in their genetics. However, they do share an environment. All right, so what I'm going to do on the next whiteboard is I'm going to write out two scenarios. I want you to read those two scenarios and then make a prediction on if that trait has a stronger genetic component, that is a component determined by heredity, or a stronger environmental component. Okay, so here are the two scenarios. The first, biological parents died before the age of 50 of an infection. The child was 5 times more likely to die of an infection compared to adoptive parents or the general population. And the second scenario is, if adoptive parents died before the age of 50 due to heart disease, then their adopted child was 3 times more likely to die of heart disease. Which one of these two scenarios has a stronger genetic link, stronger heredity link, that is, and which of these two has a stronger environmental link? Go ahead and hit pause and think about that, and then hit play again to see what the answer is. The answer is that one here, the biological parents died of infection, that has a stronger genetic link, which supports other studies that have shown that there are genes that can be passed on to our children that play a role in our immune system to help fight infections. Now, it doesn't say that the environment has nothing to do with it. It's just saying a stronger genetic link. And then number 2 here, this one has a stronger environmental link. Remember that the adoptive parents and the adopted child do not share any genetics, any related genetics. So anything that is consistent between the adoptive parents and the adopted child suggests a stronger environmental link. And this also makes sense because we know that we often eat what our parents eat, and maybe exercise like our parents exercise, or there are some similarities in lifestyles. And if someone has a high fatty diet, does not exercise as frequently, they are at risk of heart disease. Just like with this first one, the second one with an environmental link doesn't say there is no genetic link. There certainly are genetic links. It's just saying that there is a pretty strong environmental link, very likely stronger than the genetic link. Next, let's talk about twins. Let's remember that monozygotic twins, which I'm just going to indicate as MZ, these are your identical twins. These twins share approximately 100% genetics. Turns out there's a little bit more variation between the two than we used to think, but in general, it's still close enough to 100%. For our purposes, dizygotic twins, these twins, being siblings, share approximately 50% genetics with each other. At the genetic level, a dizygotic twin is the same as any sibling. Now, I'm not taking away from the fact that sharing a uterus at the same time with your sibling isn't a special connection, and there are certainly factors that have been shown to be important for that relationship. However, at the genetic level, they're 50% similar like any other sibling would be. It's reasonable to predict that when one monozygotic twin has a trait, then the other twin should also have that trait because they share 100% genetics. And anytime you deviate from that, it likely suggests an environmental component. Likewise, for any genetic link to a trait, you would predict that if one twin had the trait, then there's a 50% chance the other twin would also have that trait. And then any deviation from that, you could attribute to environmental factors. In studying twins to understand multifactorial traits, concordance is determined. And so let me define concordance. For our purposes, we're going to say concordance is the percent of twin pairs in which both twins share the trait. So for instance, if a pair of dizygotic or monozygotic twins had a concordance value of, let's just make something up and say 75%, what that means is that 75% of twins in that study, in that population, share the trait. And likewise, 25% of those twins don't share the trait. One twin has it, but the other twin does not. And what geneticists will do is they will study monozygotic twins and dizygotic twins and compare the concordance value for particular traits. So what I'd like to do now is just go over some of these data and talk to you about how we can make these predictions. So over here, I'm going to put trait, and over here, I'm going to show you the concordance values for monozygotic twins, remember the identical twins, and dizygotic twins, the fraternal twins. Acne for one of the traits. The concordance values for monozygotic twins is 14%, and for dizygotic twins, it's 14%. And what I want to do is I'm going to write some general rules. If concordance percent in monozygotic and dizygotic twins are about the same, they don't have to be identical, but they need to be about the same. And in our class, that will be within 10%. So it was 14% and 24%. I would consider that close enough. If we see that the concordance values are about the same, our prediction is that the trait has a stronger environmental influence. Again, it's not saying there's no genetic influence. It's just saying there's a stronger environmental influence. Because remember, these share all their DNA and these share 50% of their DNA. One would predict that if it was due to genetics that the monozygotic trait would be higher. But they're about the same. Okay, the next trait, let's think of Alzheimer's disease. 78% concordance in monozygotic twins and 39% in dizygotic twins. And when we see this, let's make another general rule. If concordance percent is higher in monozygotic twins, more than 10% compared to dizygotic twins, then the trait has a stronger genetic influence. Something passed on from parents to children, a gene, has a stronger effect than just the environment. Now again, it doesn't mean there's no environmental influence, but there is some. I'm going to erase these words down here just because I need a little bit more room. Huntington's disease. The concordance amongst monozygotic twins is nearly 100%. And in dizygotic twins, around 48%. Another general rule here. If monozygotic twins are 100% and dizygotic twins are around 50%, then the trait is exclusively genetic, something you get from your parents. There are always exceptions to these kinds of rules, of course, because anytime you say exclusively, you're going to find an exception. But for the purpose of our class, if you see 100% here and around 50% here, this would be your answer. Another point I wanted to make up here for this first rule, when they're similar, you say that it's an environmental effect. This happened to be that they were both low. They could both be high. You could have 80% and 83%, and you would still say more of an environmental influence. So as a review, if they are similar, then we're going to say it's environmental. If it's a lot bigger, and I know that's a vague term, but if it's more than 10% difference between the two, it'll be more of a genetic influence. And if we have 100%, then we're going to say it's exclusively genetics. For testing purposes, I'm not going to give you something that is, say, 11% from each other. I'm going to give you something that is easy to tell in this case that they're different, or in this case that they're similar. They probably won't be identical like this one is, but they'll be similar. Well, that ends this podcast and also our discussion of multifactorial traits. Throughout these podcasts, we define multifactorial traits and polygenic traits. We talked about some characteristics of them, why they're difficult to study, and how we can make some reasonable predictions about whether or not a person will have these traits or be able to pass them on to their kids. If you have any questions at all, please make sure you let me know. If not, I will see you on the next podcast. Bye for now.